Welcome everybody to the webinar of today. The speaker of today is Daniel Fuster, and he's going to talk about effects triggered by singular solutions in single bubble collapse. As usual, I introduce the speaker very briefly and then I leave him the floor. So Daniel Fuster is Directeur de Recherche CNRS at the d'Alembert Institute at Sorbonne University in Paris, and he obtained his PhD in fluid mechanics in 2007 by Universidad de Zaragoza in Spain. After two postdoctoral stays at the d'Alembert Institute and at the Computational Flow Physics Group at Caltech in USA, he obtains a CNRS research position as chargé de recherche at d'Alembert in 2010. His research career is focused on the development of numerical techniques for the solution of the full Navier-Stokes equations for both incompressible and compressible multiphase flows, contributing to the development of free software such as Basilisk, Jerris, or Paris Simulator. Daniel is interested not only in the numerical development of numerical tools, but also in the use of these techniques to improve the physical understanding of challenging problems, including multiple phases. His work includes the development of numerical models for the response of bubbles to external pressure changes, for problems related to cavitation and wave propagation of bubbly flows, as well as investigations on diverse aspects of atomization and fragmentation processes. So it's with great pleasure that I introduced Daniel Fuster. So Daniel, if you want, you can start with the seminar. I leave you the floor.
Okay, thank you very much to everybody, and thanks especially to Francesco, who has invited me to give this seminar, even if it's the same, he has not able to come finally, but I hope that at least he will profit from the talk, and we have had some exchanges. So thank you, Francesco. So as he says, I'm going to talk about some recent work we have been doing in collaboration with different people about some funny or interesting effects which are triggered by singular solutions in single bubble collapse. So the main motivation why we want to understand the process of bubble collapse is because there are some opening fundamental problems. So, for example, what is the source of damage of erosion that is induced by the collapse of a bubble? In which conditions this damage of erosion can be avoided or it can be promoted? Then there are even more fundamental questions, that is, what is the gas content of these bubbles? So we know that they are basically made of water vapor, but there are other components like gases which don't vaporize or condensate, which might have an influence. And all these can have some relation with the noise that we hear when these bubbles collapse, or more fundamentally, the response of a strongly nonlinear oscillator and the acoustic properties that these bubbles induce in a medium when they are present in the liquid. So there are many fundamental problems in which the bubble dynamics are involved. Then there are, of course, also some applications that range with bubbles of different scales. So here we just put some different scales which goes from very small bubbles at the nanoscale to very big bubbles. So for examples of very small bubbles, we put some videos of the cavitation clouds that are generated by focusing ultrasounds in specific regions of space. These waves induce the appearance of bubbles, and these bubbles collapse and induce some shock waves that are eventually used for medical treatment applications. And they are used, for example, to kill cells in the body that have cancer, so like this, or to destroy the kidney stones. The other video is just an application of surface cleaning. So in this case, basically what we do is we take advantage from the fact that these bubbles collapse and emit high-speed jets, and it also induce shear stresses to clean the surfaces. And then at very large scale, we have the problem of underwater explosion, like it can be for naval or defense applications, but it can also be an underwater volcano that explodes and that generates these big waves or big jets at the surface. And if you realize of the video, we have this first perturbation, and then after some time with some delay, we have on top of this an additional perturbation that is going to come, which is not another explosion, it's just consequence of the first explosion it happened. So it's this instance where we see that something is happening with significantly delay with respect to the initial disturbance. There is an additional interest of investigating cavitation. So in fact, it's a good test also for numerical methods. So as I say, I developed an all-math solver in Basilisk with some numerical methods that I describe here. But the question we ask ourselves is, are these methods accurate, and do they capture well the response of bubbles? So this problem is a very difficult problem and an interesting physical problem where we can test our numerical methods. And it's interesting to understand the physical problem if you want to understand what are the issues of the numerical codes. So I'm going to split the presentation into two parts. In the first part, I'm going to talk about some ongoing work we are doing in collaboration with a group of Mohammed Farad at EPFL. And in particular, is a collaboration we have with Davide Preso, who is a PhD student working on this. And in the second part, I will talk about the behavior of bubbles which are in contact with a wall. So the experiment of Davide is basically this. They focus a laser on the middle of a water container, and this bubble expands and collapses. And so this experiment is very well known. And during the collapse, we have a rebound of the bubble and the emission of a shock wave and some amplitude of the rebound. So basically, they with a camera, they record the evolution of the bubble radius as a function of time. And what is different here with respect to other experiments in the literature is that they are going to dissolve some ammonia. So ammonia is an uncondensable gas, and they can really dissolve a lot. So we can really change a lot the gas concentration in the liquid. And basically what they see is that this bubble radius evolution at the very beginning is not influenced by the concentration of ammonia. Then the bubble collapses, reaches the minimum radius, and the rebound amplitude is strongly influenced by this ammonia concentration. So this was a little bit shocking, and we wanted to understand how is it possible that the dissolved gas does not influence the dynamic response of the bubble, and we just see the influence during the rebound, and the influence is so big. So to understand this, we have or we're going to discuss the dynamics of a very simple fundamental problem that has been studied for more than 100 years now. That is the Rayleigh collapse problem. In the Rayleigh collapse problem, what we have is a bubble. We have some initial radius, and that has some initial pressure, which is much lower than the ambient pressure. So this ambient pressure is P infinity, and is supposed to be much higher than the initial bubble, the pressure of the bubble. And if we impose some simplification, so we assume that the liquid is incompressible, we neglect mass transfer processes, we assume that the bubble remains spherical at every instant, we neglect viscous and surface tension forces. In this case, the dynamics of the system are described by the Rayleigh-Plesset equation, where basically we find an ODE for the bubble radius, which as a forcing term, we have the difference between the bubble pressure at every instant and the infinite pressure, which in this problem is assumed to be constant. As an initial radius, the bubble is at zero velocity and has some initial radius. And this problem is closed if we impose a model for the bubble pressure. So for the bubble pressure, the simplest model we can build is to say that, okay, it's an empty bubble. There is no gas inside. So the pressure inside is zero at every instant. In this case, we will use as a characteristic length the radius of the bubble. as a characteristic pressure, the pressure at infinity, as a characteristic density, the density of the liquid. And we will define this non-dimensional radius, like the radius divided by the initial radius, to write this ODE that does not depend on any parameter. This is an ODE which has no parameter and gives a unique solution. And this solution is singular. So here we see the evolution in time of this radius, and we see that, okay, the bubble is going to collapse, and finally it's going to disappear at some given time. And this means that the radius will go to zero. So, in fact, the Rayleigh-Placet equation can be written in this form that we see above, where we see that the kinetic energy is 1 minus the cube of this dimensionless radius. And this equation can be integrated in time to get the collapse time. So, okay, this is already known. This is not new. We see this singular solution, and this singular solution has a well-defined time, which is called the Rayleigh collapse time, which in dimensionless units is 0.915, and that in the dimensional version is like this. So basically, this collapse time only depends on the size of the bubble, because it depends on the ambient pressure and the liquid density. But these two properties usually we cannot change. So the collapse time basically depends on the bubble radius. And I'm sorry, the bubble radius goes into the numerator. There is a mistake in this equation. So if we take different experiments from, in fact, this was the inverse of the time. If we take the different experiments in different conditions, so we have here some different bubbles that we published some time ago, and the experiments that David did, but we could take no matter which other experiments. We always manage to collapse all the experimental curves with using this collapse time and using the maximum radius. We see that the expansion and the collapse of the bubbles is always the same, and does not depend on anything. In fact, it just depends on the maximum bubble radius. What is interesting is that, okay, this equation, in fact, we can have more carefully what is happening close to the instant of minimum radius. So in fact, we can integrate the equation, and basically what we see is that the radius goes to zero with t minus t collapse power to 2/5. And then we can get also expressions for the velocity and the acceleration. So the velocity is basically 1 over the radius to the 3/2, and the acceleration is 1 over the radius to the 4th. And basically what this means is that when the radius goes to zero, we get infinite velocities and we get infinite accelerations. And as we will see later on, this is going to be very important to understand maybe some of the things we are saying. So this can be, these scalings can be verified experimentally. So here, basically, what we do is to do, they use almost 1 million frames per second to record the evolution of the bubble at the last instance when we can observe the bubble, and we see that this scaling is experimentally observed. So in fact, this very simple model that does not account for the presence of any gas already is useful to explain the results of the collapse up to the point where we can observe. Because at some point the bubble becomes so small that we cannot observe it anymore. So, okay, of course, in the experiments we see that the bubbles rebound. So we cannot say that the singular solution will be valid forever. At some point the bubble has to rebound, and to make it rebound, how we regularize the solution, we are going to put the influence of the gas or of the bubble pressure, in fact. So this is a little bit of confusion sometimes, because people try to split between the pressure of the vapor and the pressure of the gas. In fact, Prosperity derived an ODE that just gives you the evolution of the bubble pressure. So now we don't have to make the distinction between vapor and gas. This is just the evolution of the bubble pressure, and the evolution of the bubble pressure obeys this ODE. And this ODE can be integrated and to be written in this form, where basically we see that it's a constant, PV0, that we don't know, and a radio R0, which corresponds to the radius at which we measure this constant that we don't know. and the radius of the bubble. And then we have some exponent of the integral of this function, that f, that depends on the heat and mass transfer fluxes across the interface. So in the simplest of the models, if we are relatively close to the instant of minimum radius, in fact, this integral is going to be small, and we are going to recover the adiabatic gas model, where we have a constant to be fitted, which is this PV0 R0 to 3 gamma. That in principle we cannot measure. If we assume that during all the collapse the bubble responds adiabatically, of course now we can wonder if this exponent is still of the order of 1, but let's assume yes. In this case, R0 is known. We can say R0 is the maximum radius, but still this pressure of the bubble at the instant of maximum radius is some unknown parameter we don't know. So now we have two limiting solutions. We have the singular solution we were talking before, where we don't have any fitting parameter, and we have at the small times, in the right-hand side, now it's not going to be the ambient pressure that controls, but when the bubbles become very small and the pressure of the bubble becomes very large, it's basically the pressure of the bubble that will drive the bubble motion. So this is what we do on the right. But the problem of the equations on the right is that the bubble has to be really small. So we cannot really have access to this regime experimentally, but this regime has to exist if we want the bubble to exist. And then we have another ODE that we can integrate. We will have integration constants, and we can use asymptotic matching between the solutions that are valid only at the singularity, or the instant where the bubble starts to rebound, and the singular solution, which in fact is valid everywhere except at the instant of the collapse. So if we do this, in fact, we get a relation of the maximum pressure and the minimum radius that the bubble reaches, and basically depends on this PV0, which is the kind of the pressure of the bubble. If we assume that we can integrate it up to the point of maximum radius, is the pressure of the bubble at the point of maximum radius. So basically the minimum radius will, if PV0 goes to 0, the minimum radius goes to 0, and the maximum pressure goes to infinity. If there is a finite value of the gas pressure, then we have a finite value of the maximum pressure, and we have a finite value of the minimum radius. So what is interesting of these expressions is that we see that the collapse strength is only function of the ratio between the ambient pressure and the bubble pressure at some instance. So let's say the bubble pressure at the instant of maximum radius, which can be really small. So this number is huge. But there is no influence of the bubble radius. So no matter how big the bubble is or how small the bubble is, all of these bubbles, they are going to generate the same peak pressure during the collapse. And this is not new again. This was found by Rayleigh, so nothing new for now. Rayleigh didn't do it this way, but okay, you can do it in this way. And you can show that the maximum radius and the minimum radius and the maximum pressure obeys this relation within this parameter PG0 that is related to the bubble pressure. So if we solve numerically both problems, the singular problem and the problem with some amount of gas, basically what we see is that during the collapse we get good matching, but then because we have put gas, we have the rebound. But in fact, the rebound does not induce any damping. So this has no dissipation mechanism, and the amplitude of the rebound, the bubble will reach again the radius of maximum radius. So this doesn't explain damping yet. We need to try to use what we know now to understand what controls the amplitude of the rebound. To understand what controls the amplitude of the rebound, we can do an energy analysis. It's possible to do it different ways, but I like to do an energy analysis. Basically, the temporal derivative of the kinetic energy of the system plus the internal energy of the system is equal to the work that is done by bubble expansion minus the dissipation of the system. And the two energies that we can identify, there is one that is related to the internal energy of the gas that compresses and expands, and another is the energy of the liquid, which comes due to compressibility effects. So basically, it's the energy that we spend to generate waves. So if we have a shock wave, this wave contains some energy, and this energy has to be accounted for. If we assume incompressible liquid, then this energy goes to zero, and all the energy that has the liquid, in fact, is a potential energy. It will come back. This is a little bit what we see here. We have some initial potential energy, we transform it into the potential energy of the bubble, and then we expand it again, and there is no energy lost. The energy is just exchanged between potential energy, kinetic energy, potential energy at the instant of minimum radius, but there is no any loss. If we have liquid compressibility, we have a part of the energy which is lost. Okay, this equation can be written in this way as a function of the bubble volume. Basically, we see that 1 minus the bubble volume at some arbitrary time over the bubble volume at the instant of maximum radius is equal to some term that contains the kinetic energy, the internal energy of the liquid, so the energy of the waves that are emitted, and the dissipation, plus some term that depends on the gas content. So what is interesting here is that if we integrate this equation between the instant of maximum radius and the instant of the maximum radius when the bubble has rebound, in fact, the kinetic energy in these both cases is zero, and we see that the volume of the rebound divided by the maximum volume is 1 minus this energy that has been released as a shock wave, plus the energy which has been dissipated during the process of collapse. So this is very interesting now. The amplitude of the rebound is basically a consequence of the energy which has been released as a consequence of the shock wave, plus the energy which has been dissipated during the process of collapse. So, okay, we have models and we can test the model. So a very famous model is a Keller-Mix's model, or there is a slightly different version proposed by Gilmore, but it gives the same result. Basically, you can write it like this. We have our non-dissipative system, Rayleigh-Placet equation with the presence of the gas, plus a source term, and this source term depends on the local Mach number, so the ratio between the velocity and the speed of sound, multiplied by some other terms that come. For example, the last term represents the dissipation due to viscous forces. So, okay, now it's a model, and we are going to try to see what this model says. So what we do is we are going to change this bubble pressure, and we are going to make the bubble collapse. So, and we are going to write it in this non-dimensional way. So here, basically, what we see is that no matter what is the pressure of the gas we use, the collapse state doesn't change, but the rebound amplitude changes a lot. So basically, decreasing the bubble pressure, what we make is the collapse strength stronger. So the wave emissions is more important, and we emit more energy out, and we lower down the amplitude of the rebound. And another thing that this model says is that liquid compressibility effects are much more important than viscous dissipation. So in fact, I'm not going to show it here, but because we have the singular solution, we can inject it into this model, and we can capture what is the dissipation which is induced by this singular solution. And in fact, the viscous dissipation is finite, and the liquid compressibility effects is infinite. So liquid compressibility will try to dump all the energy, and this is the most important mechanism of energy dissipation predicted by Keller-Mix's models. So, so it's liquid compressibility, but then there is another important thing, that when dissipation occurs. So for this, we are going to solve this function, which is basically the dissipation. So if this function is zero, there is no dissipation, and we are going to show the evolution of this function in time. So what we see is that all dissipation occurs during the instance of minimum radius, so which is normal, because this is the point where we have very high velocities, but we have a lot of viscous dissipation. But okay, this is not the most important mechanism. The most important mechanism is the emission of a shock wave, which is also happening at this instant, because it's the instant where the pressure is very high, and when we start compressing the liquid and emitting this wave out of the bubble. So it's good. we can say, okay, we have a parameter which we cannot measure experimentally, which is PV0, which influences strongly the rebound amplitude. And we have the collapse states, which is not influenced by PV0. So what is the conclusion is that by tuning this parameter, we can always reproduce all experiments we want. So if we have an experimental curve of the radius versus time, we just have to tune the value of the pressure of the gas, and we will reproduce the experimental curve. But this doesn't mean anything, because experimentally we cannot measure P of the bubble. So this is just a way to take a model and to fit experiments. So what we wonder with the people in Switzerland is that if the Keller mixes predicts that all the dissipation basically goes into a shockwave, we can check if the effective damping, 1 minus the volume of the rebound divided by V0, is equal to the energy which is released during the collapse. So this is a consequence. This is what Keller mixes is saying. And here there is no bubble pressure. This is two things we can measure experimentally now. So we have get rid of the degree of freedom we introduce when we introduce this bubble pressure. We just say, okay, Keller mixes is built on the assumption that all the damping is consequence not of the dissipation, but of the emission of a shockwave propagating outwards the bubble. So what we do is to measure the wave which is emitted by during the bubble collapse, and the effect of concentration for every single experiment. We have an evolution of the radius, and we have the strength of the wave that has been emitted during the collapse. And what we get is this. So this is very interesting. What I'm comparing here is the effective damping on the X. So basically, one is that we dissipate almost all the energy. So as we move right into the plot, we dissipate more and more energy. And on the y-axis, we have a measure of the energy of the signal, or we can have a measure of the energy which Rayleigh placed or Keller mixes predicts. So if we start looking at the colors, which are the Keller mixes predictions, is normal. What we see is that the energy of the signal we should see should increase linearly with the effective damping D. So the more we dissipate, the lower the amplitude of the rebound, and the more energy we should get from the hydrophone. However, experimental results are very different. Experimental results are here with the dots, and they are done for different concentrations. So this small number we see in each dot is the concentration of ammonia. And what we see is that if we start looking at very high concentrations of ammonia, at the beginning is good. So we decrease the concentration of ammonia. We are supposed to decrease the value of PV0, so the collapse strength will be stronger. We dissipate more, so D increases, the points is on the right, and the signal of the hydrophone increases. So we are getting more signal out of the shockwave which is emitted. But after 0.3, the trend is inverse. And this is shocking, because now we are dissipating more. So we are still moving to the right. Moving to the right means that we are dissipating more. The amplitude of the rebound is going to be weaker, but the energy of the signal is weaker. So this is something which is completely not predicted by Keller mixes. The Keller mixes is saying if we dissipate more, is because we are emitting the signal of the shockwave which is emitted out of the bubble has to be stronger. So basically, what is telling us experience is that there is some contradiction between the assumptions that are done or the results that are given by Keller mixes and the results that we observe experimentally. And it has to be an additional source of dissipation that explains why, as we decrease further the concentration of ammonia up to 0, so as we go to air water, because 0 ammonia means air water, it's not a very fancy condition. This is the most important conditions. We have an additional source of dissipation. The dissipation due to the emission of a shockwave is not what we observe experimentally. So, and of course, before it was all tricky because you can always use PV0 to fit no matter which experimental result. So you can always argue that Keller mixes works. But when you manage to do this kind of experiment, you realize that there is something which is not working. That is the fact that is the emission of a shockwave which controls the damping of the system. So what is going on? This is something which we are working on now. And well, we were discussing with Francesco, is something which is really not obvious to clarify, neither experimentally nor numerically either, because the bubble collapsed so strongly that the radius is so small that both numerically and experimentally it's very difficult to take measurements or to correctly resolve what is going on. But still we can make some hypotheses. So first hypothesis is that, okay, the Keller mixes equation imposes weakly compressible effects, whereas we know that as we approach to water, the collapse strength is very strong, and maybe strong nonlinear liquid compressibility effects are important. Who knows? Another effect is mass transfer effect. We have neglected mass transfer. Mass transfer might influence things a little bit, but I'm not completely convinced, but okay, let's put it there. And my favorite hypothesis is spherical symmetry. So we know that Rayleigh-Taylor instabilities appear. And Rayleigh-Taylor instabilities, in fact, appear as a consequence of the acceleration. So basically, when we put a gas and a liquid, the reason why the liquid falls and the gas tries to go up is because we have Rayleigh-Taylor, and this Rayleigh-Taylor depends on the gravity, which is an acceleration. In the case of a bubble, it's exactly the same, but the acceleration is driven by the inertia. And we have seen that the acceleration, yeah.
Neglected surface tension.
Yeah.
And because when the radius becomes very small, they should be
yeah, you can put surface tension, but there is a contrary. In fact, surface tension just acts as a potential energy. It doesn't induce damping.
Yeah, but it doesn't change anything about the.
It changes at the instant of minimum radius, but it changes very little. And what is more important, it can change quantitatively things a little bit, but the physics are not changed. Surface tension do two things. First, you have to be aware that the Weber numbers are huge. So surface tension just acts when the bubble becomes very, very, very small. When the bubble is large, surface tension does not act. And so basically you have the bubble, surface tension is not important, it starts to collapse, surface tension is not important, and then you have so much inertia of the liquid, surface tension is not important. Surface tension is just important when the bubble reaches its minimum radius and the liquid has stopped. But this is over. I mean, this is okay. If you account for surface tension or not, you change a little bit the maximum pressure, but you don't change the physical understanding of the system. Surface tension might have another effect, that is the stabilization of these instabilities, Rayleigh-Taylor instabilities.
So it selects the wavelength of the.
Yes, exactly. So surface tension selects the wavelengths of these instabilities. But again, we have to be careful. This acceleration goes to infinity. Up to the point where we have experimental measurements, the acceleration goes to infinity. So you have to imagine how strong has to be the surface tension force to stabilize an infinite acceleration. It has to be infinitely strong. So, of course, as we put gas, surface tension can stabilize things more easily. So this goes into the right direction, because when we have a pure vapor, we don't have gas, the bubble is expected to compress more, and surface tension will disappear and these instabilities will become visible. If we have a lot of gas, we start stopping the bubble before, we don't reach such high accelerations, and maybe surface tension are able to stabilize the instabilities that occur. But we don't know anything. So, yes.
Gamma is the ratio of capacities, the gamma that you have everywhere.
Yes.
Capacity.
Yes.
It doesn't change when you change the concentration of various gas.
Yes, of course. All this is a model. Okay. And the gamma change a little bit. The real well, I mean, even this model if you want to do, but it doesn't change much. In fact, I mean, I've been spending my life when you do this is, but still here you need a gamma. You can put the gamma function of concentration, and you can even not use this model, but to solve the full DNS equations inside the bubble. I can promise you, the effect is so small that, and there are so strong assumptions everywhere in the model that this is really not important. And if somebody shows that is important, I will be very impressed, because my experience from numerical simulations is that, okay, yes, gamma might change from 1.4 to 1.2, but the physics are not given by this. So it's not, the temporal variation of gamma is not really important. So here, one of the things we are exploring now, but we are not given an answer, is that these instabilities might be a mechanism that becomes more important in the case of water. So Rayleigh-Taylor instabilities might appear basically here, and Rayleigh-Taylor instabilities might be here. So basically what we believe, but we have no means to prove it, is that here on the left with a lot of ammonia concentration is the shock wave that controls the damping of the bubble. And here on the right, for water, is something else. Let's say, I believe it's Rayleigh-Taylor, maybe it's not Rayleigh-Taylor, but it's not the emission of a shock wave that is modifying the trend that we observe experimentally. So as a conclusion of this first part, we have seen that a universal singular solution drives the collapse of a bubble irrespective of the gas pressure. The gas pressure only determines the peak pressures or the collapse intensity, if you want to see it. And the results of the effective damping point out to an additional source of dissipation that is not captured by the slightly compressible versions of the Rayleigh preset equation. So I think this is the main take-home message. And I think this is proven. I think I cannot tell you exactly what is the mechanism that occurs in reality, but I have a lot of doubts about the validity of Keller-Mix's models, even though if they reproduce experiments. So in the second part of the talk, I'm going to talk about the very same problem, but now for a bubbles in contact with walls. So this work is done in collaboration with an ETN project in which belongs to Stefan Zaleski, with who we funded a student that just finished last year. And I'm going to present basically the results of him. And also a collaboration we have with people in ENSTA-Bretagne, in particular the group of Michel Arigoni that is making some experiments. So, okay, first I present the experiment, it just motivates the work. In fact, in this case, what we do is to focus the laser on the outer part of an aluminum plate. So basically this laser is going to induce a shock wave that is going to be propagated into the liquid, and this shock wave will generate a bubble. So we see here the video, we see here this bubble, and then collapses. And we were interested in understanding the process of formation of this bubble. But we end up having another observation, which is very interesting. I'm not going to talk about why this bubble is formed, because even myself, I don't understand. But this is a fact, this is experimental observation. What I'm going to talk is about this other phenomena. So we were recording this at very high frame rates, but then at some point we say, okay, we are going to film everything. So now this is the full vessel we use, and this is the bubble. It's at the bottom, it's already first frame, and we are filming at very low frame rates. So before we were filming at very high frame rates to see the image of the bubble. Now this is low frame rates. And basically what we see is the bubble collapses. And then we thought that the experiment was over. We are recording a low frame rate. So in principle, we say, okay, the experiment is over. But then at some point, we start seeing this jet at the top of the free surface. And this is a very strong jet that appears with a significant delay. And this recalls a little bit the video that I put you at the beginning of the presentation, where we have this explosion, we see this perturbation. Sometimes we see the perturbation due to the shock wave, which happens almost instantaneously, but this happens at much longer times. So, and then we were seeing this other perturbation. So what is going on here? Okay, it is also related to the Rayleigh collapse problem. But in this case, I'm not going to make the bubble spherical, I'm going to make a spherical cap. When we make a spherical cap, now the geometry of the bubble is given by two parameters. Before we have only the bubble radius, now we have two. We have the bubble radius and we have the initial contact angle alpha. But we still have a low pressure inside the bubble and we have very high pressure far from the bubble. So if we do numerical simulations, I'm going to change alpha. I'm just changing alpha. All the other parameters are constant. Basically, what we see on the left, we see a bubble collapsing and a jet being directed towards the wall that impacts the wall. Whereas on the right, what we see is that this jet is not observed. What we see is a kind of parallel jet at the wall, and we end up having a mushroom-like structure. This is what simulation says. So first conclusion is that, okay, the dynamics are very different depending on the contact angle. And the interactions that happen between the bubble and the environment are very different depending on this parameter. So let's have a look at the initial acceleration field. So we said the system is initially at rest, so the velocity is 0. If we take our Rayleigh Pleasant model for a spherical bubble, we can define this dimensionless acceleration, which is the acceleration multiplied by the liquid density, the radius, and the P infinity, because delta P in any case is very large, is of the order of P infinity. And this provides, of course, uniform acceleration because the model is spherically symmetric. When we want to do this same thing for our problem, for a spherical cap bubble, and we are going to neglect viscosity again, we are going to neglect surface tension at the initial time. The initial acceleration is basically given by the pressure gradient, and the pressure gradient is obtained by solving a Laplace equation for the pressure. So we are imposing liquid to be incompressible substance, and then to solve this Laplace equation for the pressure, which gives you the initial condition for the pressure, we have all these conditions, boundary conditions for our problem. So, okay, this is the solution of the Laplace equation for the initial time. So basically, what we see is two very different patterns. To make it simple, here I show the pressure gradient isocontours. So they are the acceleration isocontours. So basically, if the angle is lower than 90 degrees, the acceleration at the contact line is 0. So this is very, very funny because we don't have viscosity, but still the contact line doesn't move. The acceleration of the contact line is 0. So even in the Euler equations, the contact line will not move, and the acceleration at the top will be maximum and going downwards. If we go to angles that are larger than 90 degrees, in fact, we see here a huge concentration of acceleration at the contact line. I recall you is Euler equations. We don't have viscosity. So in fact, we observe that the acceleration at the contact line is infinity. And the acceleration at the tip is still A0, is the same acceleration. But now we have a very strong acceleration going in this direction. So what is going on? In fact, if the solution of the Laplace equation has been investigated for this configuration for other different problems, and people propose, or well, it can be shown that the 3D problem can be reduced to a 2D problem, and the solution of the 2D Laplace equation can be written using a system of coordinates that is sitting at the contact line in this form. So we have coefficients, Ck, R is the distance to the contact line, power to Bk, and Bk is a coefficient that depends on the angle. And there's cosinus of Bk multiplied by theta. So with this structure of the solution, we have that the acceleration R0 obeys this, and this solution is singular when the angle is larger than P by half, and goes to 0 when the angle is smaller than by half. So again, we have here a singularity, but now it's a singularity at initial time, not at the final time, as we saw before. Here we have a singularity at the initial time at the contact line. So we can check this numerically. We compare just the theoretical formula with the numerics, and we see here, we parameterize the acceleration of the interface as a function of this angle. and here is this angle in log scale, and this is the acceleration in log scale. So basically, we change the contact angle, and we see that the acceleration goes to infinity as we approach to angle to 0, so as we approach to the contact line. And the numerics are in very good agreement with the first term of the series of the theoretical expression. Once we have this first series of the expression, in fact, we can use just the first term of the series to integrate the acceleration all around the bubble. It's quite crazy, but it works. So we get this average acceleration of the bubble, and with this average acceleration of the bubble, we can reconstruct the far field pressure. So it's kind of asymptotic matching, but it's not exactly this. And here there is no fitting parameter. So this is just the singular solution we got. And from this singular solution, just assume that it's a punctual source. If we look far away from the bubble, we can reconstruct the red curve that in fact reproduce very well the pressure field far away from the bubble. So we have this far field pressure that then matches with the near field pressure through this matching, which is imposed by just conservation. So, okay, we have the singularity identified at the initial time, but there is still a more interesting thing, that is that we have a stress-free, more or less, we have a free stress condition at the free surface, so the bubble can be seen as a free surface, and this implies that at the initial time the vorticity is going to be -2 over the radius of curvature, the derivative of the radial velocity with respect to theta. So the velocity at small times is related to the acceleration. And basically what we see here is the slope, this derivative is different depending on the angle. So in one case it's going to be positive, in the other case it's going to be negative. And okay, this is known. The interface can act as a source of vorticity. But then the sign of vorticity is going to be reversed. So in this case, we are going to generate region of positive, negative. In this case, we are going to generate negative, positive. And in the liquid, the vorticity is just diffuse. It's not either generated or destroyed. So basically, during the process of bubble collapse, we expect to have a vortex dipole, to form a vortex dipole of this type. And this vortex dipole is known to propagate upwards. This vortex dipole is known to propagate downwards. So here is not only the jet that is going to be directed towards the wall, but it's also a vortex dipole that is going to squeeze against the wall, whereas in the other case, we expect a vortex dipole to be propagated upwards. And this is a little bit what we see in the simulations. If we make a simulation now run for a very long time, we see the emission of the vorticity field, and we see this vortex dipole that is emitted upwards the bubble. And now it starts to become clearer what is going to happen in experiments. So we put some ink at the bottom of the tank, and we see this vortex dipole being emitted after the collapse of the bubble. This vortex dipole can propagate for quite long distance, and finally reach the free surface and generate this jet that we have observed before. So I thought that it was very interesting because this is kind of people that has investigated the collapse of a bubble close to a wall, they are very focused on what happens close to the wall. But here we saw that, okay, a bubble collapsing close to a wall can have influence at very long distances compared to the bubble radius. So I was thinking that, okay, underwater volcano explosions can generate tsunamis. They didn't like it, but I think it's possible. and just the last thing to tell you is that in fact this energy equation we mentioned before, we can apply it. In fact, it's valid always. It's not valid only for spherical bubbles, but it's also valid for non-spherical bubbles. So another way to derive the maximum pressures is to use this equation. This equation, if we assume that the bubble volume is very small at the instant of minimum radius, can be written in this form. So this is the maximum pressure, and this is the term derived by Rayleigh, the last one. And before we have like a penalization term. And it's very interesting, this penalization term. This is something which is going to decrease the maximum pressure we reach. We identify the internal energy of the liquid, so the energy that is released by the shock waves, the energy which has been dissipated during the process of bubble collapse, but we also have the kinetic energy. So when the bubble is spherical, at the instant of minimum radius, the kinetic energy is zero because the problem is spherically symmetric. But when we have a non-spherical problem, the residual kinetic energy is not necessarily zero. And this acts, in fact, as a penalization term of the maximum pressures we can reach. What we see here is this velocity field at the instant of minimum radius for bubbles with different contact angles. And we see that, okay, this velocity field is never zero. We can quantify it, and we see that the kinetic energy, as a function of this time, zero is the collapse, goes to a maximum, then it decreases, but it never reaches zero. So there is always some residual kinetic energy that is there that acts as a penalization on the peak pressures we reach. So this is done for different pressure amplitudes. Here, what we do is we plot this maximum pressure obtained from numerical simulations as a function of the angle. So basically, the straight line is the prediction we have from the theoretical model. The red point, the blue points are the numerical simulations, and the green points, sorry, are the theoretical subtracting only the kinetic energy. So basically, the difference between the theoretical pressure and the red points is the penalization on the peak pressure reached by the bubble due to the fact that the bubble is not spherical. And the difference between the red and the blue correspond to the influence of liquid compressibility on the peak pressures. So we see that for bubbles that are far from 90 degrees, in fact, it's these non-spherical effects that mainly control it's just the first order correction, because the zero order correction is really the Rayleigh collapse solution is good, but as a first order correction, we have this non-spherical effect. But okay, this is true for the strengths we have used. So here we are trying to see what is the impact now on the strength. So now we vary the strength, the colors are the angles, and again, the black line is the theoretical prediction, and the Rayleigh collapse prediction, and the dots are the simulation results. And what we see is that, okay, maybe for small pressure amplitudes, the black line is the first order correction. But as we increase the strength of the collapse, it's less and less clear that the black line is going to be right. And the problem is that in simulations, we only trust things up to 15. But in experiments, if we make a bubble collapse in water, and we assume that the bubble pressure is around the vapor pressure, we get a factor of 50. So we are very far. Here, this point here is very far from what happens in real conditions. So maybe the Rayleigh collapse pressures are not valid at all, even at zero order. So just to conclude the talk, we have seen that in the case of a spherical bubble in contact with a wall, there is a corner singularity that exists only for angles for open bubbles larger than 90 degrees. The physical effects are very different from the classical bubble collapse. And an upwards jet is observed, and the influence of the angle and liquid compressibility on the peak pressures and bubble collapse is clarified. Thank you very much. If you have questions.
So thank you, Daniel, for the very interesting and detailed talk. So I would say, as you just said, let's open the stage for questions. So whoever wants to ask a question, just let's check in the seminar room if there is someone.
Yes, there are questions.
Okay, so let's go for the seminar room first.
The second part in the experiments, can you observe the compressibility effect in the liquid with a technique like shear run or something like this? There are short waves which propagate.
I guess somebody can do it, yes. But yes, I'm not experimentalist, so I cannot. I guess yes, because if they see it in the single bubble collapse, but okay, maybe they are not much interested on this, or if somebody's interested, I think it will be interesting.
Illustrative to another point of comparison with numerics. Or...
Yes, I fully agree. Yes.
For experiments, how do you reveal the volume of bubble?
From experiments, they do that. I'm not experimentalist again, but I think they just take the image and they.
The figure about the conversation between the theory analysis and the experimental data, right? In the end of the part 1.
But the bubble is spherical. They just need to measure the radius. You mean these plots?
No, for the slide. Yes, here. Yeah.
No, here, well, here you have to be aware that this is the energy. There is no radius here. Well, the radius, if you want, is here. We just compare the volume of the bubble as rebound with the volume, but no, there is no. What I'm not sure to understand what.
How do you get the for doing experiments? How do you get the dissipation data? Is that you calculate?
No, it's not. This is. I don't like to call it dissipation. It's damping. Because it depends on the volume only.
How do you measure the volume during the experiment?
The volume, you just take the image. Is the volume at the instant? Is the volume between this and this? It's very easy to measure. The problem is measure the bubble volume here, but the bubble volume here is very easy. I mean, at the beginning I saw you just take the image, and then if you have a scale. You measure like this.
That's I think during the experimental at the final stage, experimental.
But there is no special. No, it's not the. No, you don't understand. It's not the final stage. Here the damping is between this instant and this instant. I don't need to measure here.
Okay.
The thing is that when we integrate this equation. This is the volume, the bubble volume during the rebound divided by the initial bubble volume. So we get rid of the volume at the instant of minimum radius.
Okay, and that times for the volume for the laser times volume. I think. Do you observe that the bubble is still as spread?
Yes. In fact, they do it very small. To make the bubble sufficiently spherical but even if it's not perfectly spherical, the error, believe me, is much smaller than the big variations we have on the volume. But you will see. It expands, and then at some point it reaches quite a spherical shape. I cannot tell you, maybe there is 10% error. I'm being very, but 10% error, this huge difference is not 10% error. Believe me, it's huge. So the volume, I think I'm not experimentalist again, so I don't know how they compute this, but I have the feeling that the volume is measured quite accurately. I have not many doubts about how they measure the volume. But if you have, I mean, again, I'm not experimentalist, so.
Do you think that really closer when you reach the really small radius of the bubble at the first collapse, would it be possible that you have the formation of at small scales of more bubbles and then coalesces?
Yes. If you have Rayleigh-Taylor instabilities, I think this is what happens.
And can these come into the computation of the total energy that you have shown?
If you start taking into account fragmentation, then it's a mess, because basically it depends on how many fragments you generate.
Yeah.
And you don't know how many fragments you generate. You can do analysis based on Rayleigh-Taylor, but the problem is that people don't even observe Rayleigh-Taylor. So it's very difficult to say to which extent Rayleigh-Taylor theory. If you make Rayleigh-Taylor calculations, you get that the bubble breaks into millions of fragments. But still, the experiment, you don't see millions of fragments. But of course, millions of fragments maybe happens for very small times at very small scales. And then these fragments coalesce again, and then you see again a spherical bubble. But we don't know. This is all science fiction.
Yeah, sorry, I will one of the questions. So if I well understood, you do exclude any non-ideal gas effects.
No. Well, no, I don't exclude anything. If you want to put here other things, you can. You can put other things here I have not think about. The only point I'm trying to make is that maybe Keller mixes, or maybe no matter which model you use, it's not because you reproduce the experimental radius in time that the thing is right.
Yeah, I see. Thank you.
Yes.
Okay, is there someone else in the room who would like to ask a question? Maybe you can tell me, Daniel, if there is someone.
No, I think it's fine.
Okay, so then I think we can open the stage for questions also for the virtual participants. So if there is someone who would like to ask a question, just feel free to unmute your mic and ask the question. Yeah, Christiane, go ahead. Yes.
Okay, hello. I'm Christiane Lechner from TU in Vienna, Austria. Thank you for this very interesting talk. I have two questions concerning the first part. The first one is that maybe I didn't get it, but the ammonia, how does it enter the bubble? Do you know? I mean, is it there already when the bubble is generated? Because it's distributed everywhere, and so it's also in the initial bubble, or does it sort of, is there diffusion, or how does it come?
Yeah. Well, we don't know, but
okay.
In principle, the ammonia is uniformly dissolved into the liquid, and then when they impact with the laser, of course, the part that has been vaporized, the ammonia is there, and then maybe there is some diffusion of ammonia. What we can say is that the ammonia diffusion has no much influence, because if we look at the expansion of the bubble, is the same no matter what the ammonia concentration is. So if it will be a process related to diffusion, the maximum radius of the bubble will be controlled by ammonia concentration, but it's not. So I think we don't know how ammonia enters the bubble, how much enters due to the initial vaporization and how much enters due to the diffusion later on. But I think from experimental results, we can say quite safely that the amount of ammonia that initially is vaporized is much more important than the one that enters due to diffusion. That ammonia still changes this PV0 sufficiently in a sufficiently important manner so that the amplitude of the rebound is modified by this. So yes, but all this remains a hypothesis. I think this is the only consistent explanation, but of course, I mean, we don't know.
Okay, thanks. And then the second question concerning this first part would be, you're comparing Keller mixes and Gilmore, or Keller mixes with the experimental data. But did you also do computations with Basilisk of this setting? And because then you know something about the nonlinearity, right?
This is very interesting. So I do compare Keller mixes with my numerical method, and then my numerical method matches with Keller mixes, and then I was so happy. But it's true that all the simulations I do that I can trust, they are done for not so strong conditions. So in fact, Keller mixes, when the collapse is not so strong, I mean, I never seen somebody reporting Rayleigh-Taylor instabilities occurring at the last instant of the collapse. And I think the main reason is that the bubble has to collapse so much that it's almost impossible to capture numerically this. Because if you want to capture the instabilities that occurs during the last instance of the collapse, we will need to refine at the instant of minimum radius, maybe to put 100 points per diameter. So this is just impossible. Nobody can do this. So I think that numerically what happens is that we always kill the scalar Rayleigh-Taylor instabilities because we don't have enough resolution, and we get good agreement with Keller mixes. So because basically it's all weakly compressible and there is a spherical bubble and all the assumptions of Keller mixes hold. But this doesn't mean that this is what happens in reality. In reality, something different could happen. So yes, I think this is something very interesting for numerics and very challenging problems that maybe we will not be able to solve anytime soon. That is to really capture well what happens when we have a strong bubble collapsing and it reaching its minimum radius, because it's very difficult.
So we have seen instabilities for very strong collapses with open form, and then when the bubble re-expands, then it stabilizes again. So the rebound is spherical again. Yeah.
Yes. Yeah. But this is also observed in experiments. I mean, the fact that the bubble is stabilized, this is fine. This is physical and this is normal. But the thing is how the dissipation mechanisms are modified by these instabilities. But maybe these instabilities are not important for the dissipation. I cannot tell you. Maybe is the equation of a state that is really controlling this. I mean, I would like to think that they are Rayleigh-Taylor instabilities, but yes, I have no. The only thing I can tell you is that with these experiments that the EPFL people did, it seems clear to me that we cannot explain this with current numerical simulations. And neither with Keller mixes model, because
also not with Basilisk, so not with the full simulation.
with Basilisk, okay. No.
Okay.
But in Basilisk, I have to emphasize the fact that we are not able to reproduce experimental conditions. So and it's not only I can do experimental conditions, but I need to do experimental conditions and to put 100 points per diameter when the bubble reaches its minimum radius. It's really, I think it's really impossible, but maybe somebody can do it. I don't know.
Okay. Okay. Thank you.
Yes, you're welcome.
So thank you. So let's see if there is. If there are more questions from the virtual audience. Just once again, feel free to unmute your mic if you have a question. That doesn't seem to be the case, so maybe I can ask you a question, Daniel. So it's I would have a question related to the last problem you presented, in which there was a sessile droplet that becomes that originates singularities of pressure for the condition of the droplet having an angle of a pinning angle smaller.
It's a bubble.
The bubble. Sorry, bubble. Yeah, sure. And so my question is about. I mean, what about the pressure, the temperature there? I mean, are there like clear relationship between the singularity in pressure and the singularity in temperature, and how does this play a role on the ideal on the equation of state for the bubble?
Yes. So here there are two things when you talk about the temperature. In principle, if you assume that the bubble is adiabatic, the temperature is related to the pressure. So if you increase the pressure, you increase the temperature. Then you have to be careful, because at the interface, when we do numerical simulations, we know that the heat capacity of liquid and also the solid, it will depend a lot on what the solid is. So it evacuates heat and it absorbs heat very efficiently. So in fact, usually when we do simulations, when we account for the heat transfer, the temperature at the interfaces drop a lot. So if you are thinking into the temperature of the interface between the gas, so the temperature inside the bubble is going to be very high. But if you think about the temperature at the interface between the solid and the gas, it will depend a lot on the thermal properties of the solid. So if the solid conducts heat well, or at least as well as liquid, we will have a very low temperature. And if it doesn't, then it will not transfer much heat. So the temperature is going to be low anyway. So as far as I know, the temperatures they measure at the solids, at the walls, are always relatively small. You can reach a temperature increase of few degrees, maybe 10 degrees maximum, but inside the bubble you will reach very high temperatures. So yeah, I mean, it's a little bit, there is kind of discontinuity of temperature at the there is no discontinuity, but kind of, there is a very thin boundary layer, thermal boundary layer between the wall and the gas.
Okay, yeah, that's very clear. But under these conditions, I mean, so how does the contact line is supposed to work? I mean, because there, I think that's that you are setting like a pinning condition, right?
No. Here in the simulations we did both. We did simulations where we're pinning the bubble, and we did simulations. In fact, some of the simulations we did were without viscosity, so the contact line can move freely as it wishes. And yes. And this is also, well, something. This is what I told you before. It might be interesting because we see that the dynamics of the system might be depending on the shape of the bubble. Here, basically, what we saw in this very simple setup is that the dynamics of the collapse are very different depending on the angle. But now, if you make this bubble expand and compress, then the shape of the bubble depends a lot on how the contact line moves. So maybe the physics of the collapse, when you account for both expansion and collapse. And so, for example, I know this a paper from Lesnar, the person who talked who asked the question just before. She was doing this. She was expanding a bubble and then making it collapse. And she didn't observe the same thing because basically during the expansion, she formed a boundary layer between a viscous boundary layer between the liquid and the wall. And the bubble shape at the instant of maximum radius is very different from the shape I have here in the slide. So when she makes the bubble collapse, the collapse dynamics is completely different from this. So you can imagine that now if you change the solid or you change the way the contact line moves, this shape at the instant of maximum radius might change depending on the wettability properties of the solid or the conditions you put in the simulations. And so I think there is a lot of things to do to clarify the role of all these parameters in experiments first, but also in numerical simulations.
Okay, perfect. So thanks for the explanation. So I would say let us allow for a last question because there is a reply from Christiane, and then we close the seminar because we need to give time to Daniel to get back to the training. So Christiane, go ahead.
You know, just a remark, because you said it's so different if you expand the bubble and then it collapses very differently. But there's a close similarity because I think it's sort of this flow focusing that you have a higher curvature at the outer boundary, which you in some sense also have because the flow converges there, and that's why it's faster from the side. So we also have this inflow from the side, which is horizontal and parallel to the wall.
But I'm not sure. The main thing is about this vortex formation. I was not sure that you because we did simulations very similar to yours, and in fact when we do simulations similar to yours, when we expand the bubble and we make it collapse, we don't observe this. This is changed a lot, in fact.
You mean the vortex is changing?
The vortex emission,
okay,
yes.
Okay.
And so we know that when we make the bubble expand and collapse, it changes a lot. But what happens in experiments the experiment is much more complicated, because in experiments we see all a vapor. We don't have a bubble. It's like a bubble being formed from the wall. We don't have a bubble we don't have a bubble that expands. We really have a bubble that is formed from the wall, and all the wall is full of vapor already. So I mean, it's more realistic for us to start a simulation where the bubble is really in contact with the wall and we don't expand, we don't simulate the expansion, because to simulate the expansion correctly, I think we need phase change, and we don't have phase change. But even, yes, we don't even understand why the bubble is formed. So that's still another thing. So yes, I think really the shape of the bubble is very different, and it's not trivial what is the initial condition you have to put. So yeah.
Okay. Thanks.
Okay, thank you very much. So thanks again, Daniel, for this very interesting and detailed talk. And as you can see, it kind of triggered a number of interactions, lively discussions. So thank you once again.
Yes, thanks to you, Francesco.
Thank you. And so I invite the audience to thank you once again, and hope to see you soon next week. Thank you.
Okay.
Good evening.
Ciao, ciao, Francesco. Bye.
Bye.
Thank you. Bye.
Thanks for you coming. It's very weird.